Добрый вечер. Когда я ничего не слышу.
Так, добрый вечер.
Добрый вечер. Ну, я постараюсь сделать на iPad. Давно еще не презентовал, и вроде бы я разобрался, как его подключить. И даже как, в общем, как менять страницы, подсвечивать что-то лазером. Вот. Надеюсь, все будет нормально.
Так, ну что, слышно?
Да?
Привет. Да. Миша в каком-то странном тумане на картиночке.
Более интересный вопрос, не подвисла ли она полностью при этом.
Нет, а я не знаю, да, действительно, никакого движения не происходит. А вот сейчас происходит, но все равно в тумане. Нет, наверное, ты заплевал камеру. Да, я думаю, что иначе этот
Ладно,
туман
уж
не объяснишь.
какая разница-то, ничего.
Нет, никакой, нет. И слева черная полосочка еще есть. Добрый день. Oh, hello.
We should switch to English, right?
Yeah, I guess it's better.
Well, when should I start?
No, let's see. No, there is a hope that some usually people we start later a bit, just let people come. But I don't know what Vereshchagin. He was yesterday at this school at HSC, so I don't know whether probably he returned. But let's see. But this is recorded and automatically, and then we will anyway will post it. Yeah, okay. I think Danya is coming. Yeah, I think we can slowly start.
Okay,
If
so
someone will come in next few minutes, probably.
yes, I think we'll still be on the first slide with the definitions, with the problem formulation. So, hi everyone, my name is Gleb, and I'm going to talk about robust mean estimation problem. So this is one of the central problems in robust statistics, and especially algorithmic robust statistics, because in many settings there are differences between what we can do inefficiently and what we can really compute in polynomial or quasi-polynomial time. But today I'm going to talk about the version of the problem where there exists a polynomial time algorithm, even though it is non-trivial, and some trivial generalizations of one-dimensional algorithm don't work. Still, this problem that I'm going to talk about today, it is not computationally hard. So I start with the problem formulation. So suppose that there is a distribution in some d-dimensional space. We don't know anything about the distribution. Later, I will tell what is the assumption that we will use. But so far for the formulation, we don't know the mean. And suppose that some sample is generated from this distribution. So the input, what we are given is some corruption of this sample. So basically, there is an adversary, and this adversary chooses arbitrarily, as the adversary wants, chooses a set of size at most epsilon n, and then arbitrarily corrupts the samples corresponding to this set. So basically, what we know is that there exists some large subset of samples that comes from that exactly is exactly equal to the original sample. And there are also some corruptions that are completely arbitrary. So,
But what is the order? First arbitrary chooses the set S, and then things are corrupted,
yes.
and then the real data are generated, or the real data are generated.
No, close the data. More difficult. The adversary sees the data, and then chooses the set and chooses how to corrupt. Yes. So the set is not random. So the set is also. So it is already non-trivial even if the adversary removes something. So even if the adversary just removes some samples, it already can really change the mean, and that's why we will see that we cannot hope to get the same error as without the adversary even. So okay. And the goal is, of course, to compute as accurately as possible this mean. We want to efficiently compute it because in many formulations, many different variants of this problem, there's really a difference, as I said, of what we can efficiently compute and inefficiently compute. So today, I first explain how to compute it inefficiently. It will be not that hard. And then I will show how sum of squares method can be used to basically use the proof of the identifiability proof of the inefficient procedure in order to design an algorithm. So also, in some sense, it will be not only a talk about this problem, but also about the sum of squares method.
Yeah, but let's first look at the trivial case when.
Trivial case will be on the next slide. Yes.
Okay.
But if you want, yes, we can discuss also. Yes.
Yeah, no.
Coming, so
If just S is 0, then is there something better than just taking the average? Or
no, what do you mean? S is 0?
no,
You
S
mean,
is never. There are no errors. Just
no. Okay. Yes. Then basically, yes. I mean, it of course depends. Yeah. It also depends on what exactly do you mean by the best. But yes. I mean, it is not actually true that always for all statistical properties the sample average is the best. But actually, yeah, I mean, here we're working in the regime where sample average works perfectly without the adversary. But of course, if the adversary is allowed to corrupt only one sample, already sample average is very bad because Even one sample can ruin everything.
Yeah.
So then some assumptions. So first, that epsilon is small enough, so we allow epsilon to be constant, some small constant. Basically, we should think of epsilon as something tending to 0, but not very fast. So maybe something like 1 over log of the dimension, or maybe 1 of the dimension to the power 1 over 10, something like that. So I mean, it is not necessary, but it really helps, especially when we compare different methods.
But you mean for given n, epsilon is also fixed. It doesn't change with
Epsilon, yes, I mean
time.
it can be that the epsilon is constant. So for example, 1 over million, let's say.
Yeah.
Or it can be that epsilon depends on n or on the dimension.
Yeah. But for fixed n, it's some constant. It doesn't become bigger or
Yeah,
larger.
but we will not. Yes.
Yes. For every n, there is some epsilon n, and we assume
we
that it
assume, yes,
decreases.
exactly. We assume that epsilon is known. Let's say that epsilon is also given to us. Epsilon is some kind of an upper bound. The adversary doesn't have to corrupt everything or to corrupt actually anything. So it's some upper bound, and we assume that we know it. So So our assumption in this talk that basically makes the problem solvable in polynomial time is the following. So we assume that there is a finite covariance matrix and just some scaling assumption that this covariance matrix has spectral norm at most 1. So here I clarify this thing. That means that if I multiply it by a unit vector from both sides, I get at most 1. So this is basically the spectral norm, the definition of the spectral norm is maximum of all this unit over all unit vectors. So basically, so in one-dimensional case, I'm going to talk about one-dimensional case right now. So in one-dimensional case, it corresponds to the case. So our assumption on sigma corresponds to we just say that the variance is at most 1. So
and if we have, for example, I don't know, 2 coordinates, this is equivalent. The finiteness is equivalent that the both variances are at most 1, or it's not enough.
What do you mean by both variances?
Both for first coordinate and the second coordinate. Finite.
No, it is not. It is. Yes, I mean, for 2 coordinates, it kind of is, but for many coordinates, it is not. So it is stronger assumption. It is
so you can have every
small. It is possible that the variance in every coordinate is small, but the spectral norm is large. It is possible. So basically, you can think of a matrix, of a covariance matrix that has, let's say, diagonal is equal to 2, and all other entries are equal to 1. I believe this should be an example. So the variances are equal to 2, and the spectral norm is actually very large. It grows with the dimension.
Yeah, but still, it's all covariants are finite. Then the spectral norm is also finite.
Yeah. This is true. Yes.
But it is just not some constant depending on it.
Yeah, but yes, I mean it is important.
Yeah. No, I'm just asking because I have no
exactly. Yes.
I never.
Yes, it was a really good question. We here bounded by 1, and of course there are it is possible that, let's say, all the variances in all entries are bounded by, let's say, 1 or 2, I don't know, and then the spectral norm is actually super large. So we do not consider this case. We exclude this case because in this case the error is actually large, and it is not possible to make it small. So, okay, so now one-dimensional case. So basically, in one-dimensional case, there's a very simple procedure, what we can do in this case, and this simple procedure is optimal. So we just remove epsilon n largest samples, epsilon n smallest samples, I mean, of this corrupted data, and then compute the average of the rest. And I'm not going to talk about why it works. It is not very hard, but also not so trivial. So it works and it has errors. For some reason.
Yeah. So intuitively, it's clear that it seems for the average, if the adversary knows that we will take averages, it makes sense to try to corrupt this average by adding something on one side.
It is maybe not that clear why it's exactly root epsilon.
But why it's indeed maybe more complicated corruption takes into account this algorithm and tries to.
Exactly. I mean, it doesn't matter. Of course, the adversary knows the algorithm. The adversary knows.
Yeah. So it's not really obvious, but still
It is not
interesting.
obvious, but I mean,
Okay, let's
we will see. I mean, I'm not going to talk about this because I will show an estimator that works also in high dimensions, and it will have also the error root epsilon. So that's what we'll see. It of course also works for one-dimensional case, and we will anyway see it. And of course, when I say root epsilon, of course, epsilon should be not very small because like it cannot be zero, right? The error cannot be zero just because there was also statistical error, even without the adversary. So, but in order to avoid this statistical error, I will always assume that number of samples is large enough. So if number of samples is large enough, then statistical errors are not very.
Yeah. And can you explain why, intuitively, why it's square root of epsilon, but not something else? Or it's difficult to understand.
I mean, okay, I can explain. Well, I mean, intuitively, because we, okay.
Just intuitively.
What do you mean by intuitive? Maybe let me first show you, yes, it is because we can kind of use Cauchy-Schwarz, and basically root epsilon comes from there, but it is probably not what you mean by intuitive. Maybe let me show you
Okay, okay.
A lower bound. And the lower bound will show that we cannot go beyond root epsilon. That having error smaller than root epsilon, at least asymptotically smaller, let's say even root epsilon over 10 is not possible already. So this example showed if we have all mass, we have two distributions, and I claim that we cannot distinguish between them. So if the first distribution just is always zero, it's just like a distribution that is supported on one single point, zero, and the other distribution is a mixture of this distribution with weight 1 minus epsilon and another atom 1 over root epsilon with probability epsilon. So in this case, so you can see it here. The parameters are computed. So here everything is trivial. Here everything is also not very hard. It is easy to compute the moments here. So the mean is root epsilon. The variance, basically, this variance just 1 by 1 matrix here. 1 minus epsilon, so it is smaller than 1 and satisfies our assumption. And what is the problem? The problem is that we cannot distinguish between them, because what the adversary can do, the adversary can basically, if we are in the first case, the adversary can just replace, I don't know, take a random subset of size epsilon n, or roughly epsilon n, and put set these samples to this number, or the opposite. If this is this mixture, then basically the adversary can just remove all of these numbers and set them to zero. And then it is not possible to understand what was the case. And
so the choice, why it exactly the root of epsilon, is because we want the variance to be about 1. Of course, we can just take some large value with small probability, but if the value is too large, then its variance will be big. But here we have this kind of balance.
Exactly.
Yeah.
Exactly. Yeah. So as I said, like I hope that this is already some kind of gives intuition why we have this root epsilon here. But of course, it does not explain why this procedure works and gives and achieves this error. So this lower bound does not give. So okay. So I hope is this clear? Are there any questions so far?
Yeah, indeed. Maybe someone wants to ask something. What is the statement of the problem, what we are trying to do, and what is the promise, more or less?
Yeah, so this is basically just, so one-dimensional case is not very interesting because there is really a simple procedure. And this procedure, and it is optimal, of course, not only when we assume that the variance is finite, also lots of generalizations. Let's say, for example, for Gaussian, if we assume that the distribution is Gaussian, the original one, then of course better error is possible. It's possible to read after error epsilon. But this procedure is actually not optimal for Gaussian case. It would lead to error something like epsilon root log 1 over epsilon, something like that. So a little bit suboptimal for Gaussian case. For Gaussian case, the best possible thing to do in one-dimensional case is just to take a median. So this is just maybe some more insights to give some more intuition about this problem.
Yeah, it's intuitively clear that the distribution is important, and this one specific distribution which you showed is just especially bad because it just looks like a small fraction artificial errors added to something quite simple. So
okay, so let's go further. So high dimensional case. So in high dimensional case, things are more complicated because if I just do a trivial entry-wise generalization of this, so I apply this method to each entry, I of course get additional root defactor just by Pythagorean theorem. So, and it is actually not clear what we can do in high dimensions in order to get rid of this. So, so in high dimensions, we use high dimensional assumptions. These assumptions are a little bit different from classical statistical assumptions. So here we assume that, so usually in statistics, we somewhat assume in classical statistics that.
So this trivial entry-wise generalization, let me check that distant So we just take for every coordinate, we take the biggest data in this coordinate and smallest elements in this coordinate and discard them and take the average. But
Yes,
then this biggest and smallest elements can be different, of course, from different coordinates.
Yes, exactly.
So it's a kind of
in every
strange thing.
entry, we get error root epsilon. And then since we have d entries, we should multiply it also.
Yeah, in every coordinate. Yeah.
In every coordinate, we have error root.
Yeah.
Yes. So now high dimensional assumptions, as I said, are a little bit different from classical statistics. So here we don't assume that d is fixed, and then n is something very, very large compared to it, or goes to infinity. So here we really want to restrict n. It can be larger than d, it can be reasonably larger, but it cannot be super large. So we want it to be polynomial in d. So then again, so we want, I mean, it is not necessary this assumption, but for simplicity, we'll use this assumption so that everything is polynomial in d. So also 1 over epsilon, and the bit complexity of the input. Of course, like we are given when we are talking about algorithms, we are not given like, let's say, samples from normal distribution. We are given like some part of it, of its decimal representation, and we say that the bit complexity of this part is at most polynomial in d, so which is a pretty mild assumption.
No, it's stop. So the first is kind of strange. It seems that the bigger we have n, the easier is our task. If we want to get some error which depends on epsilon and d, bigger n should be better or worse. Why?
So bigger n. Okay, so there are two things. Of course, bigger n is better. Bigger n is actually not a problem if you are talking not about computational issues. Bigger n is never a problem here. So anyway, whatever happens, we have just remember that we have error root epsilon, whatever n is, and if epsilon is constant, let's say, so I can increase n arbitrarily and still I get error root epsilon. So the error here is not like it doesn't have this statistical nature. It always will be constant if epsilon is constant, say. Or if it is a very small subconstant, it will be super slow. So will tend to zero super slowly. So and here, so why do we need this, for example? Because imagine it is not very hard to design an algorithm that in exponential that can use, let's say, a linear number of samples in D, and in exponential time computes the mean or like the estimator.
Yeah.
But we want, but by this assumption, I want to avoid this, because basically, if we give, if we say, okay, n is allowed to be exponential in D, then basically I just read just some part of input, apply this kind of not very sophisticated exponential time algorithm, and then I get a nice estimator, and it is polynomial in the size of input. And this is what I want to avoid. I want polynomial in the size of input to be polynomial in D. So this is what I want.
Yeah. And what I don't understand, what is bit complexity? The entries are just numbers.
We are given like bunch of vectors, right? And each vector, like there are d entries, and the entries, of course, it has subdecimal representation, right? I mean, we are talking about real algorithms here, like Turing machines.
Yeah.
So of course, when we are talking that we are given samples from normal distribution, we mean that okay, we have a decimal representation, and then the tail of this representation is removed, and then we work only with the initial segment, and this initial segment is allowed to have length.
So it's not about the structure of the inputs. It's just about the precision, how many digits.
Exactly. So we just, again, it is not very important, but when we talk about running time, imagine that it is exponential in D again, like we have one entry has like this. It is very simple. I was not going to talk about it too much. It is
Okay,
just some
okay.
technical
Yeah,
condition.
yeah, okay.
Nothing interesting here. So of course, if you want to be more precise, we can include a parameter bit complexity and formulate everything also bit complexity. For simplicity, I assume that everything should be polynomial indeed. So and then if this assumption is satisfied, then there exists a polynomial time computable estimator such that for some large enough, let's say d cubed, I don't know, like or d to the power 10, some fixed polynomial, then with probability tending to 1, we get optimal error root epsilon. So
and this is under the same assumption that the matrix is the covariance matrix is just
yes, of course, yes. Otherwise, otherwise it depends on what assumptions do we use.
yeah.
It can be either better or it can be worse, yes, depending on what.
Yeah. So for fixed D, we do not get anything new compared to one-dimensional case. The real
Exactly.
achievement is that the dependence on D is not in this constant of square root of epsilon.
Yes. And of course, we cannot go in high dimensions. We of course cannot do better than root epsilon because basically this one-dimensional example also works in high dimensions, right? So root epsilon is the best what we can achieve. Okay, so now again, so I'm not going to discuss it too much, but just let me first get rid of everything statistical, like of probabilities and etc. So basically, what we are going to do, okay, maybe I can also announce like this. So we are going to estimate not the true mean, but the sample mean of the original uncorrupted sample. And if n is large enough, of course, by some basic statistical theorems, this thing should be very close to like root epsilon. It can be much smaller than root epsilon, but root epsilon is enough for us. So if we can estimate the sample mean of the original sample up to error root epsilon, we are done if we have large enough number of samples.
Yeah, so this original samples is just includes not only the values which are not non-corrupted, but also the values which are just masked by these corrupted values. So it's just a full original sample.
Yeah, exactly, full original sample. Yeah.
Because otherwise it will also depend on the choice.
Yeah, exactly. Otherwise it will have some other. Yeah.
So we take the original sample, and if we take just the average, then kind of standard Chebyshev bound says that more or less this happens.
Yes, exactly.
And because we can do this.
Exactly. Yes, and of course this is also kind of a law of large numbers, or so that we can assume that covariance, if it is polynomial, like n is polynomial indeed.
Yeah.
We can assume
So it's kind of general probability theory, and we can.
Yeah, exactly. So nothing here, nothing interesting here, and basically, that's it with statistics here. So like for today's talk. So now we are going to estimate something really specific and deterministic. So and we will get error root epsilon independently of whether we were lucky or not. Whatever happens with this, no, of course I'm right.
It's still with high probability.
Yeah. So as long as this property is satisfied, the second property is satisfied. So we will be that close of from the sample mean of the original sample. But it actually doesn't matter. Imagine that this event happens, but super unlikely event happens that this is not satisfied, then we still, with our procedure, we will be that close to the sample mean, but of course far from the true mean. But this happens only with very small probability. So, okay, so now everything.
Let me just understand it better. So you say that there are some non-probabilistic requirement for the sample, and that say that if we change epsilon fraction and then apply this procedure, then we get something close to original average, independent of which part we change.
Yeah, exactly. If this event happened, so if the original sample, yes. So even if it didn't come from any distribution, but we take this formally empirical covariance and it satisfies this bound, then yes, our algorithm gives us something root epsilon close to the sample average of the original data.
Ah,
Yes.
yeah.
So no probabilities anymore. So for this pattern for this one. So
Yeah, so more or less, you have a set, and then which is not too largely too big, and then you want to find the averages, and then the adversary deletes or not deletes, but of course changes epsilon fraction of points, and you don't know which points are true and which are not. Not can you somehow still compute approximate the original average?
yes. I mean, if yes, exactly. So as long as again, so we need to know something about to assume something about the original data, right?
Yeah.
So we assume this, and if we assume this, then we get this. Yes.
And before we have just a very simple idea, just ignore the biggest element because they can be corrupted elements.
And of course, this also works. Yes, this is of course also true about the previous, like the one-dimensional procedure. So this is
Yeah,
of course true also about this procedure.
yeah,
So as long as, I mean, this data satisfies this empirical covariance of the whole data, let's say empirical variance is not very large, it's smaller than 2,
yeah.
then this procedure works, yes. Even if
And
the
then the
results,
stupid thing, the naive thing which we can do now is just take the elements with biggest length and ignore them because they try to they look most suspicious. But this is not in every coordinate, but just in Euclidean length. But this
yeah,
is not
I
what
don't think it can work because
it's.
imagine that all of
It's
them
not a
are,
good idea.
that all of them are, yes, exactly. Imagine that the original distribution was uniform over some sphere. And then the
Yeah.
adversary also corrupts them just by doing something on this sphere. So then they all have the same length. But still the adversary can really change something.
Ah.
Yeah,
Yeah, so
so
if
not that
we
way.
add new epsilon fraction of new point near some point of the sphere, this will change this
Exactly.
will move average to epsilon. And so there are no reason to delete, they are not bigger than others, but still they change.
Exactly. They change the averages.
Yeah. And of course, if we see such a distribution, we will be very suspicious why there are so many elements near some
We
point
also
that
don't
probably
know.
they
Yeah,
are
I mean,
corrupted.
we also don't know. Somewhat yes, somewhat yes. Our assumptions, of course, do not allow us to do not allow some crazy inputs. But of course, here somewhat this is what happens somewhat here. Of course, this is like some very large point, but in some sense, you can assume that this is like okay, they are all on the sphere, and this is just some kind of mass near some
Yeah,
point.
maybe
It
the
also
real
could have
distribution
happened
is
in the
just
little.
also has a part which is near some point and other part which is uniform, and then it's quite something quite natural. So we cannot.
Yeah, but again, we do not use any assumptions except the assumption on the covariance. So we cannot say, okay, the distribution looks suspicious. This is what I mean, as long as the covariance is nice, is bounded, we should be able to work with the distribution.
Yeah, but this is not dangerous because but if we have just epsilon fractions of element concentrated in some points of the sphere, then adding them or deleting them changes the average only by epsilon of epsilon, which is up for now. Now it's completely okay. So
No, but why?
still deleting the largest elements may be not such a stupid idea, no?
But why? Okay. Why you say it is epsilon? It is not clear to me.
No, we have no the average
Which sphere do
original
we?
average was
Okay,
0.
what is your sphere? What is the radius of your sphere? Because we have, for example, we have this, when we have this, the radius of the sphere should be something like root d. Because like, if the covariance is, let's say,
I thought about a unit sphere actually. So
but then the covariance is super small. So basically we want, let's maybe normalize everything so that it is, if it is like, if the covariance is identical.
yeah.
I mean, I don't know if some really simple procedures can, I mean, the procedure I'm going to describe, okay, it is definitely not simple. It is sophisticated and it refers to some really difficult things. But there is a simpler procedure also based on the same idea that I'm going to describe. So yeah.
Yeah.
But still, you need this simple idea, which basically is here. So this lemma, it basically
Yeah.
says the following: that if we have some bunch of points such that they differ from from the points of y only in at most epsilon fraction of entries, and the sample covariance, so basically just this thing, is bounded by 2i, 2 by identity matrix, so basically it's small, then it should be close to the original, to this thing. So in some sense, if we have, if we have, note that this x also satisfies this property, right? So this x, we can, if I plug instead of zx, they are satisfied. But what I'm
No,
saying,
you are too fast. Sorry. So just explain what are this X, Y, and Z. I am lost.
Okay, so before we had x was a true sample. Maybe I can actually
True sample X1, Xn.
we had like x1, xn,
Yeah.
and these guys, they satisfy these two properties. So the first property, just by definition, y is a corruption of x. So I mean, of course, if I instead write here xi instead of zi, and of course, if I write here, so xi here, then
No, so we start with the true sample X, and then there is a corrupted sample Y,
yes,
and then we try to make some reconstruction of that. We don't know X's, but we have Y, and we do something. We try to find some S prime with some property.
exactly. We try to find them. Let's say we are computationally unbounded and can do whatever we want. So we are doing brute force over all subsets. And also maybe, let's say, we try to guess what can be the values of x on other, like on the corrupted samples, and try to compute this thing. So basically, like from the beginning, it was not obvious that if someone gives us x from the very beginning, then we can say, oh, that's fine, that is actually a good x, and now I take sample average and output it. So how could we have checked it from the very beginning? It was not clear, but it is actually possible from what I'm saying here. So
Yeah.
because basically, if we just check these two properties, I mean, this property, like we kind of don't need to check depending on our procedure, of course, but and this property, we just do brute force and check this one. Then as long as we have it, we just output the sample average, and it is a good estimator.
So if we are find a subset which has small covariance, then we know that this subset provides a good estimation if we just take.
Well, we need to do something a little bit more. We need also to set somehow missing values. But yes, what you are saying is
So this DI
what you are saying is
also
possible.
exists. We are allowed to change some ways.
We are allowed to do anything, yes, so
But
far.
we need
They're
to
not
imagine, insert something which gives small. Okay.
Yes. So basically, this is like, so if and this is how we can actually, so let me also formulate. So yes, some procedure like let's remove something, and then it is possible to say like how exactly should you set these values, and it also works. But let me also formulate it like in a little bit more abstract manner. So let me write down this polynomial system. It looks scary, but basically, I mean, I will discuss like what happens here. But the solution to this system, because of these properties, the solution to the system is root epsilon close to mu x.
No, so what is
I'm
this
going to discuss
system?
in more detail. So the system basically just encodes. So wi encodes the indicator that zi equals yi. So we are trying to find zi.
So the double I is wi is just 0 or 1.
Yes, exactly. So this encodes that this is just 0 or 1. Yes.
Yeah.
So this encodes that at least, or let's say 1 minus epsilon n fraction of them. Let me put here equality.
Okay.
So so that 1 minus epsilon n of w's are actually 1.
Yeah.
So then here it says that wi is exactly the indicator. So whenever these guys are equal, so whenever these guys are not equal, this should be 0.
Yeah.
So then this is just a technical, I mean, it's not necessary to write it, but just I introduce a variable for this mean and just write that this is indeed mean, I mean.
Yeah.
Yes, and this is kind of the most complicated thing. This is here we encode this condition. So we say that the empirical covariance should be smaller than to identity. And how we say that it is smaller, we just introduce new variables for some and construct a PSD matrix from them.
Okay. Yeah. The smaller means that the difference is positively, not negatively definite.
What is nice about this system is basically the solution would be, what would it be? So here we definitely know that Wi should be an indicator that these guys are equal, right? So then this Z would be some tuple of vectors, and we know that this tuple of vectors satisfies this, the empirical covariance.
Yeah.
And basically that's all. So basically this means by this lemma that this mu Z, the solution, should be close to root epsilon. So of course,
no, this means that any solution of the system,
yes, any solution of the system is a good estimator. Yeah.
Good estimator, but you claim that it's somehow optimal or what?
Optimal, yeah. I mean by good I mean root epsilon. And
yeah. So you don't claim anything except that this of epsilon.
I don't claim anything except that this is root epsilon.
Okay, you can say like this. It's not exactly unclear
I mean,
for me why it helps.
Basically, so kind of, if we were interested only in some estimator in the existence, as soon as we prove this lemma, we are done, right? So we don't need. We cannot, of course, efficiently compute the solution to this system. We cannot find it efficiently, but some, like let's say, exponential time. I think for this specific system there is an exponential time algorithm that solves this. Yes, but of course, and that would be, we would be done, but of course we are interested in.
But you don't claim that some, I don't know, semi-definite programming can be somehow used or whatever.
I claim exactly this. I claim exactly this, and this is what we are going to do next.
So we can.
Yes, the sum of squares is always semi-definite programming. There is nothing more.
So this is why you consider the system.
Yes, exactly. I'm considering the system exactly because of this, and because I'm going to illustrate the method. Of course, after, like, from this lemma, if you have this lemma, you also can provide actually something somewhat simpler than what I'm going to discuss today, a bit simpler, but something that, like, why I'm discussing sum of squares, also first because it is interesting, and second because if we try to generalize this to some other distributions, or not generalize, but to investigate what happens if we, for example, assume something else. Then for many classes of distributions, nothing better than sum of squares, and not only better, but nothing except sum of squares is known. So to provide to achieve error better than, let's say, root epsilon. Okay, so this is, so okay, so we have, okay, so the proof, okay, the proof is going to be actually to be hard. So I'm not sure if you want to have. So probably we started late, right? And maybe we should have a break later, or
no. Usually we can just continue until everyone is dead. But it's not the. But okay. just maybe you try to explain how it's proven or what is the idea.
Yeah, no, exactly. Yes. So okay, one thing is that this proof. So first, already an announcement that this is going to be a sum of squares proof. So I'm going to provide a proof that actually turns out to be a sum of squares proof. So it already satisfies also, it is not only a mathematical proof, it also satisfies some additional properties. So of course, you may say, okay, why do we need the fourth power here? I mean, those of you who will follow the proof.
But if you want us to understand what is sum of squares, you shouldn't assume this.
No, but I mean, I'm going to use exactly the same proof. So later when we come to sum of squares, I will just show the same slide. Or I mean, very similar.
So it's enough to understand that this has some specific property.
Yes, but it is not only if you understand this proof, and then later if you understand, okay, the steps of this proof indeed satisfy those properties that we that sum of squares proof should satisfy, then yes. So basically, okay, let's start. So we know this this difference. This is exactly what we want to bound. So the norm of this U and this difference.
Yeah.
Then we denote the indicators let's denote this one by alpha, and W we already kind of denoted it in the system. So W is this indicator, and alpha is this one. So now I just take the fourth power of this, of the snow. This is equal. So now I just don't do anything with this U, and I'm not going to do it till the very end of the proof. So this will be just this U, just some vector that we.
So it's strange. That's U, and you once you write it as mu x minus mu z, and other time you write it as U.
Yeah, exactly. I mean, I'm not sure. I mean, it is strange or not, but I mean, the proof works.
No, yeah, okay, but you are allowed to do this, but just it's not some misprint, but just intentionally it's written in two ways. Okay.
Yeah. So, yes. Now what we're doing is also quite simple. I just subtract this stuff and add this stuff. So just let's say I just so okay. So this okay. Maybe I should be a little bit more. Yes. We just
No. So when you take this scalar product, it's just a number. So
Yes.
xy minus zy u is just a number, and this number is strangely.
No, sorry. I think yes. Maybe I made some mistake. Let me see.
Yeah, I have a question.
Yes.
I didn't understand the statement of the lemma. I thought it was a typo and y is equal to x. But can you say again what is difference? Like there is y, x, and z, and
But
x.
I let me try to explain how I understand it. So there was some x,
Yes.
which was the
Sample,
sample,
like the
original
true,
sample.
yeah.
And there is some y, which is the corrupted sample by the adversary. So adversary changed some epsilon fraction of the elements, and it's corrupted. And we are trying, our goal is restore the original thing, original average. And for that, we decide, we have a guess. We have some z, which is this corrupted y, which we try to somehow uncorrupt. So we also replace some epsilon fraction of its element by some other z. Of course, it may be different epsilon fractions and different elements. So we have three things: uncorrupted things, corrupted things, and a potential restoration value sample, potentially restored sample. We we are making a wild guess. Let's decide that this and this and this and this values were corrupted, and it should be instead. It should be this and this numbers.
Okay. And assumption one says that the z differ from x and at most
from y,
epsilon
Yeah, but
at epsilon fraction, and therefore z differs by 2 epsilon from x.
Yes.
Yeah, it differs by 2 epsilon from
I
x.
didn't understand how it could be possible, but now I understand it. Okay.
But so the idea is that originally this covariation matrix was not large for x's because it's assumption for our distribution, and after the enemy changes the sum values, of course it can become bigger.
Sasha, and what was the original assumption? Also with 2 times I.
Yes, the original assumption was just I, but since we are working with sample, we need to have some kind of. It can be also 1.01.
So this is the relaxed assumption.
Yeah, this is the relaxed assumption because we say, okay, with high probability, our original sample satisfies this with 2I.
Yeah, so we know that there exists some, because original sample was assumed with high probability it was good, then we can assume that there is a way to change some elements to get small covariation.
Sasha, but what is the assumption about the original sample? Only that it coincides with I.
it has covariation smaller than I.
And it coincides with y in
Yeah, it
1 minus
coincides with epsilon probability, 1 minus epsilon probability, it coincides with y.
So here
Oh.
probability is only in the choice of the random I, and that's it, right?
No, there is no probability at all. here
Okay,
in the
no
lemma.
probability at all. Okay.
So there was something with a small matrix, with a bounded correlation matrix, and enemy changed things. And we make a candidate for restoration. Of course, this candidate of restoration should, if it was original thing, it should have small correlation matrix. But imagine we succeeded in doing this and find some z. Then theoretically, maybe this z is completely different and still has small correlation matrix. But no,
But
the
because
lemma
of the
says
assumption 2, it is impossible.
no. Assumption 2 says that z looks probable as a restoration.
Right.
Because correlation matrix is small as it was for the original sample. And then the lemma says that we can be happy because we can now use average of this corrected sample and get something close to the average of the original sample. So we don't actually need to guess the original sample and to guess what really was the wrong values and what was the correct values. If we can make some kind of plausible correction in the sense that this we change some small fraction of values and get small covariation matrix, then this plausible correction is good to get for the can be used for finding the average.
Yes, exactly. So this kind of simple property that X satisfies is actually enough for us to say that, okay, our candidate Z is close. So there is no other option. If it satisfies this property, it should be close to, the average should be close to X.
And now I suddenly see in corollary, the matrix B, we can always choose it to be 0, right?
No.
No. Sorry. Okay,
No,
my mistake.
so
Sorry,
it's a
forget
covariation
about
matrix.
it. Yeah.
And when we say this smaller or equal,
Yeah.
it's understood that
I
the
got it.
difference
Yeah.
is
Sorry.
positively defined.
Yeah.
So corollary doesn't say anything really additional. It's just the lemma.
Yeah, but let's
Nothing
focus on the
changed
proof.
here.
Yeah, okay.
Yeah.
Okay, so let's see. Okay, so you
Okay,
claim
then there is some strange thing. So we can.
you claim that there is something strange, but what is strange here? Let's see.
No,
So
strange is just first. It's a bit strange that we compute the square of the norm of the square of the norm. So we take not the u squared, which would be logical, but
yeah,
u
this
fourth.
is exactly what I told you. Just don't. I mean, this will be important later. Yes, you can of course in this proof you can of course start with 2, but of course I can also square everything in my proof. And
Yeah, okay. No, you have the right. Then you write this thing in a strange way. The same vector mu x minus mu z is once used as written as u and one used as mu x minus mu z. Okay.
so yeah, so this is like the missing step, I think, right? So this is equal to this, right? Sorry, I mean,
Yeah, it's just
it's hard for me to write because it is not exactly.
it's just the same, exactly the same number xi minus zi scalar product with u, and it's written with very fancy coefficients, but the sum of these fancy coefficients is just 1 because for that is divided by n, and for each I we have some.
I mean, this is just the definition, right, of this.
Yeah.
This is
No. It looks no. It's just you are trying to do very strange things, but you have it's correct.
And it's called the proof, you know. I mean, I'm trying.
Yeah.
Okay, this is equal to this. And here, of course, I just add and subtract the same thing. So this is not very sophisticated. Okay, so now this, I'm going to the next slide and this will be removed. And now note that this is 0. So why is this 0? Because, okay, alpha, recall that alpha is this indicator, wi is this indicator. So when they both are not zero, it means that what? That y equals to xi and y equals to z, yi equals to zi. It means that xi equals to zi. And it means that this is zero.
Yeah. So this is more or less, this is just, this indicators mean that you, there are some parts of the sum which are correctly guessed in both. So where the restoration is made in the place when there was an actual error, or if the restoration was in a place where there's no actual error. And this is okay.
So now Cauchy-Schwarz. So just, okay, so we only look at this now. This is zero, so we have this guy. So this is a product of two things. And then just using Cauchy-Schwarz. So basically, okay, so just for those who don't remember, I can write. Let me just write it with expectations, because it is like, you can assume that sum with coefficients 1 over n is just some expectation. So you can say that f g is bounded by e f squared by e squared. So this is, I mean, this is, of course, this is just standard Cauchy-Schwarz. This is just about
Yeah.
this is not like some fancy Cauchy-Schwarz that we are going to use later for.
Okay.
This is just the standard one. So now this guy is just equal to this guy, right? Because this is either 0 or 1. It is 1 minus product of indicators. It can be either 0 or 1. So that's why square, I can get rid of it.
Yeah, okay.
So then this thing is at most 2 epsilon. Why? Because this thing can be 1 when either this is not true or this is not true.
Yeah, except for two epsilon fraction,
Yes.
all three vectors coincide because we twice made an epsilon.
Yeah.
Yeah.
So here it is 2 epsilon. Here I did not change this part at all. So this is okay here. Now I'm going to do something here. And again, you will tell me that it is super strange and weird. I just add u and subtract u. Yes, I'm doing this. And then what I'm doing, then I say, okay, so u is basically this thing. So I can just say, okay, so plus, I just plug it outside. So it goes here, this plus term. And then the minus term, I just say, okay, it is minus mu x. And I put it together with x, so x minus mu x. Minus multiplied by minus is plus mu z. And that's why, okay, it is like minus minus mu z. Basically, I mean, it is easier probably for you to just look at it and understand that it's true than for me to. So again, like plus goes here, and we only are left with this minus u, and u is again equal to, so again, it is like minus mu x plus mu z. And so you just need to verify.
Yeah, okay. No.
Verify actually, this is. Again, this is not a sophisticated step. I'm not doing.
Yeah. No, that's just the problem. It seems that you are just making some rewriting.
But this is not
in a very strange way, and this
Not,
somehow.
I don't claim this lemma is the most interesting thing. Of course, you can.
Okay.
The most interesting thing is that we take this technical proof and say why it actually implies the existence of the polynomial time algorithm.
Okay.
So this will be okay. I mean, we don't have so much
okay.
so that I cannot. But I mean, unfortunately, I have to show you exactly this proof.
Yeah.
So of course you can see. I mean, in the core of this proof is the Cauchy-Schwarz. So in the end, we will take of everything, and that's why this guy will be under the square root, and that's why we will have square root error in there.
Okay, so let's see what you are doing then.
Yes, then I just do again Cauchy-Schwarz, or just so because this is there are 3 terms, right? This is like plus 1 multiplied by this guy, minus 1 multiplied by this guy, plus 1 multiplied by this guy. and I just plug 1 plus 1 plus 1 square, sorry, 1 squared plus 1 squared plus 1 squared multiplied by this guy, which is the sum of squares of this.
Okay.
Again, Cauchy-Schwarz. Or, I mean, here there are just 3 terms. You can explain it in many different manners. And I also don't care if it is like 6 or any other constant here. It's completely fine. Just
Yeah.
basically that I can, if I have constant number of terms, I can plug squares inside and bound it by some constant. So this is, okay, so this is just the definition. So this is the definition of of the covariance, of the empirical covariance, let's say.
Yeah.
So again, I have this guy, right? And this comes this. So again, like this sum of this comes this, and this is of course like just
Yeah.
no.
Okay, and then you say that it's bounded by because of
Yeah, because of our
function?
assumption. Yeah, so this one is the original sample, which is bounded, and this one by our assumption, by the statement of the like the
Both are bounded by 2 because there were 2 in both cases. So we have
yeah, this was our assumption in the lemma that this is
yeah.
bounded. This is exactly the single place where we use it in cookies.
Okay, and we have the same 4th power of u, which is in the left-hand side.
Yes, exactly. But now it is multiplied by something small, right? 6 epsilon.
So even if it's there, we get some non-trivial bound for
yeah. So 6 epsilon is negligible compared to 1, let's say. We assume that epsilon
Yeah.
is less than 1 over 100.
Yeah.
So, no, sorry, why? Yes, so this. Okay, so now we get this, right? Because again, I take this here, so I get 1 minus 6 epsilon. So 1 minus 6 epsilon multiplied. 6 epsilon is multiplied by this. And here I get, it is less than 24 epsilon by this square. So this is what we have. And basically just by dividing by this norm.
Okay, so if we don't have this u4 in the right-hand side, it will be just what we want. And u4 is not important because the 6 epsilon coefficient is anyway small compared to 1. So even if we move it to the left-hand side, we still get some.
Yeah. So now you can have a look at this proof, and maybe you can say, okay, why is it like again in the core of this proof, we have like why exactly do we get square root? Because we use this Cauchy-Schwarz here. Because and Cauchy-Schwarz we use because we want to use the second moment bound. Basically, the same proof would work if I assume, like, let's say that the 4th moment bound, then I would use here the 4th power, then I use here the 4th power, and then here would be something a little bit more weird, but with the 4th power, we would get in the end epsilon to the 3/4. But of course, it requires assuming the 4th moment, which is a stronger assumption. So if the 4th moment is bounded by 1, I mean,
so epsilon, if the 4th moment is bounded, we can do a better thing because it's a stronger additional assumption.
Exactly. With exactly the same
epsilon
with
3/4. Yeah. So if all moments are bounded, we can just have epsilon in any power close to 1.
Yes, exactly, with any power close to 1. But if you, for example, sub-Gaussianity, so that the moments are bounded like the moments of the Gaussian distribution. You get in the end epsilon by square root of log 1 over. Yeah, so something very close to epsilon, not exactly epsilon, but something close. But of course, it also requires more samples. So like because we need the moments to concentrate. So here for the second moment concentration, it is enough to have like something close to linear in the dimension. If you want the 4th moment, we need quadratic in the dimension and so on.
Okay.
For example, if you want really quasi-linear in epsilon, we already need super polynomial number of samples. This kind of violates our assumption, which is not like what we want right now, but just.
Okay, so is it more or less clear, or there are some questions, or what?
Yeah, this is purely algebraic proof, and I apologize for this, but
I mean, all steps are clear. Right?
Yeah. And Sasha, is it okay? Yeah. Okay.
But somehow I missed where we use the exact definition of alpha I and WI.
Oh, okay. Let me try to explain. So we have actually we have points of indices of several types. Sometimes just this original xi was not changed, and we don't change it trying to reconstruct the value. These are very good indices. And the bad indices when either the adversary changed the value or we changed the value. And when the adversary changed the value, we say that alpha I is 0.
Sasha, wait a bit. Do we
Yeah.
use only the fact that the difference, Hamming distance between y, between z and x is 2 epsilon?
Yes, we use. What do you mean
Only
by
this. So we do not need actually any intermediate y here.
If you want, yes, if you say we want to simplify this proof, yes, you're right. Yes, we only need to use this. Yes, exactly.
So
But
actually we never use alpha I, wi individually. We are just looking at the product of them.
Exactly. Yes. Yes.
So the lemma can speak only so the lemma can be explained like if we change 2 epsilon fraction of values, then the differences and still have the small covariation matrix, then the average cannot change much.
Yes. Maybe I
So
should.
y is a purely intermediate thing, and it never appears in our Cauchy-Schwarz things. We just have x and z. So its appearance in the lemma is just a pure way of saying things. Just we make two changes. Actually, we can speak about one change from the original way to probable reconstruction.
Yes. Yes. This is true. Yes. But I mean, this is true. So we could have simplified this proof by saying that alpha I wi.
Yeah, we can even simplify the statement by deleting all the y's. It's just a statement about x and z.
Yes. Yes.
Yeah, that's what Kolmogorov says.
Yes. But we still need it in the end because we have this, for example, as a variable of our W.
Yeah, of course we are given y's.
Later we will
Not-
need this. Later we will need
If
this,
we are
yeah.
not given access, but the
But I
оправдание.
think the way I did it, because you see, you figured out the idea, and still I can use exactly the same proof later.
Yeah. Okay, so Bruno, is it okay?
Yes, I got all steps and everything clear.
Okay, let's then, if no one asks something, let's continue.
So, okay, now like the most mysterious part of the talk. So now a little bit more about these systems of polynomial equations. Suppose we have a system, and let's say m equations, k variables, and then let's say we have two polynomials of degree L in these variables v, and we say that there is a sorry, I think I fixed. No, we don't need this g here. I think I just reformulated it.
Yeah.
So we have a proof of the inequality f is greater or equal to 0. Degree L sum of squares proof from this polynomial constraints P. If for some polynomials of degree at most L over 2, and some other polynomials such that for each of them multiplication by corresponding polynomial pi from the system has degree at most L, we have this. So basically, what does it mean? Let me say again, and then you can try to find an idea. So this is the sum of, so we can represent it as, okay, I will say a little bit wrong thing right now. So we can represent it as a sum of squares of polynomials, and these polynomials, these squares have degree at most L, and an element of the ideal of this system of degree L. And this is, of course, not exactly true. If I said it like this, this would be not true. So I not only want an element of the ideal, it is, of course, an element of the ideal, and of course, has degree at most L. But I need each term here to have degree at most L. So And why does it make sense? Because if I have any solution of the system, if I plug it here, what do I get? I get here f of v. Here I get some square, which is non-negative, and here I get exactly 0. So basically, on the solutions of the system.
Yeah, but let's start from the beginning, because I heard it many times. But so imagine we have some inequality which says that some polynomial of x1, x, y, and z, for example, is always non-negative, like an inequality between, I don't know, average and quadratic average, or whatever, some inequality. And then there is a way to prove this inequality just by an equality. If this polynomial is equal to sum of squares of some other polynomials, then of course it's always non-zero. And then just tell us, so is this the general way to prove that polynomial is non-negative everywhere, or it's not always possible?
It's not always possible.
Not always possible.
Moreover, yeah, it is well known, and even I think already Hilbert knew everything about this question, like when it is possible and whenever not, he knew the criterion.
So there are some cases when f is still everywhere possible, but cannot be represented as sum of squares.
Yes, but this is exactly why Hilbert asked this question in this. Don't remember the number of the problem, 17th maybe problem. So about the rational functions. So every rational function, if it is positive or not negative, it can be represented as a sum of squares of rational functions. And
no, it should be positive. No, rational function should be also positive if it's sum of squares. So you say that if a rational
converse, I'm talking about the converse. If it is positive, it is represented as a sum of squares.
Yeah. So if it's strange, so some polynomial, if each polynomial is a rational function, so if we know that this polynomial is negative, we always are able to prove this explicitly by writing some equality of f as a sum of squares of rational functions. But what we cannot have polynomials. So it's important that we have some rational functions in hi, even if it's not. But is there some simple example why it happens, or it's not?
I mean, there is an example that is pretty simple, but there was no single example like before 60s, I think. There is an example. I don't have it right now here. But...
So what is difficult?
Wait. Do we consider real valued polynomials?
Yes,
we always speak about real values.
Then x squared plus x plus 1, for example.
It's very easy. It's x. It's in the middle school. They learn that it's x plus 1/2 in squared plus a 3/4.
No, with one variable polynomial.
Выделение полного квадрата.
I see. Sorry.
X plus yeah.
Yeah, and by the same reason, for one variable polynomials, it is also easy to generalize. For one variable polynomials, it is always true. Yes, sum of squares.
Yeah, for one variable polynomials, because we can factor it as a product of
exactly.
Quadratic polynomials, and each quadratic polynomial cannot change the sign because it's never always non-zero, and so we can present each quadratic polynomial with this с помощью выделения полного квадрата as a sum of squares. And then we multiply everything and get the sum of squares. But it's funny that there exists some very specific polynomial f, and probably...
and it is not very hard to prove, actually. Even it is not very hard to prove, yes.
It's known that for some reason it cannot be represented of the squares of polynomials, but on the other hand, we can explicitly represent it as a sum of squares of rational functions.
Yes.
But it would be nice to look at this polynomial, but it's another story.
Well, I mean, we can. Each of us can search it, right? I mean.
Yeah. But it's interesting. How can we prove that it's not a square of polynomials, or how can we find this polynomial? Interesting. But still.
I mean, proving that it's not a square of polynomials is. I mean, okay. I think there is also a way to do it easily, but of course, this is an algorithmic procedure. There is a way to say, like, if a polynomial is a sum of squares of low degree polynomials. Okay, it is about low degree polynomials, but there is a way definitely to prove that.
Yeah. But so there are still some other remark that we are looking at a conditional equality. Conditional equality says that if our variable satisfies some polynomial equations p1 is 0, pm is 0, then something is some f is non-negative. And of course, this can be shown by adding this term in the right-hand side, which goes to 0 if all these equalities are true. And so this is a special way to prove this conditional polynomial inequality.
And this is already a different theory, because there is also like, okay, what you are talking about, for example, what you were talking about, this positive polynomials which are not sum of squares, and kind of for good domains, for good algebraic sets that are solutions, or for good polynomial system, let's say, it's better to say about systems, not solutions. For good polynomial systems, it kind of is not happening. I'm not going to formulate a theorem, but kind of everything that is non-negative is sum of squares. Or let's say everything that is, I think we need some slack, maybe everything is that is positive, or maybe larger than some epsilon, is always larger than arbitrary epsilon, is sum of squares, as long as some mild assumptions from the system are satisfied. But these assumptions in particular imply compactness. So they essentially
but wait a bit. But for this general conditional case, there is also a version of this solution of Hilbert's problem. If we don't make any restrictions, we can always prove if we allow hi to be rational functions.
Yes, I mean there's not like this yet. There is a way to write it down as a single theorem that would imply, in particular, like the sum of squares. Like the theorem that says that, okay, for that would imply the solution for Hilbert's problem about rational functions, but I think would also immediately imply something good for good systems.
Yeah, and for example, it's a strange question, but still, if we somehow proved the same thing, but not for f, but I don't know, for f cube, then f cube is equal to sum of squares plus these things.
Mm-hmm.
So it will also imply that f is non-negative.
Mm-hmm.
But it looks like something more general, because we just can multiply everything by f square.
No, we cannot. I mean, we cannot take the root here.
So f cube is generally more general
things. Yes,
general things, but we don't allow this. And still we have additional restrictions now, that the degree L sum of squares is a proof which first use polynomial, not rational functions. Mm-hmm. And second, all the things, or the auxiliary polynomials h and this g,
yes,
should have small degree L.
Yes. So every term involved should have degree at most L.
Yeah. Okay.
So yeah, so we write whenever it happens, whenever there is a sum of squares proof that f is non-negative of degree L, we write it like this. So similar to the, I don't know, to first order logic, let's say. But we have this index L here. Mm-hmm. So then, of course, I mean, we can use also this notation, meaning that f minus g is non-negative. So this is, I mean, everything what I write.
Okay. This is just.
Yes. So then some properties. Okay, so the first property is quite easy. So if we have two inequalities, we can sum them up.
Just we add sum of squares and add these polynomials, and the degree doesn't increase.
Exactly. This is a little bit harder. So if you have, I mean, also easy. If you have non-negative, if you have a proof that f1 is non-negative and another proof that f2 is non-negative, then there is a proof, and the degree of the proof is sum of these degrees, that their product is non-negative.
But it's a bit strange, because which hi have, if we just take a product of these things, then yes, we take we multiply hi by also by this the sum of squares is multiplied by the second type of terms.
Yeah, there will be like 4 terms, right? There will be 4 terms.
And let's look at the cross terms.
Yes, the very first term is not problematic, it is a sum of squares. And all other 3 terms, they go to this part.
But Sasha, P is the same, so all of them will be divisible by some PI.
No, I'm saying the stupid things. We multiply HI square by GJ PJ. And
Okay.
HI square. Ah, they have L over 2. Sorry. So this.
Yeah. I mean, of course, we need a little bit.
Yeah. This I
Otherwise,
didn't
it would be
realize.
impossible. Of course, we need to sum the.
For H we have stricter thing. Yeah. Okay.
So then this is just an easy corollary of this. So basically, if I just, if I have, so I can multiply.
Yeah. You can multiply by. Very good.
This is an easy corollary if I just apply it to f minus g. This one.
Yeah.
Okay. So, okay. Now, kind of the dual objects to sum of squares proofs, let's say, and let me be a little bit informal. And now let me be formal again. So, a pseudo expectation. Yeah, it's a little bit. I mean, I'm not going to give like a lot of motivation. Why do we call them pseudo expectations? I will say something. Not sure how motivated you will find it.
But what is P calligraphic P? What is
this? Is our system. Let's say we fix.
Yeah. This is not F,
but
this
still
is
work
variety.
Of polynomial equations. We have P. There are like M equations, K variables. Like we fix for these couple of slides. So then we have a degree L pseudo expectation. It is a linear functional that is defined on the space of polynomials of degree at most L, such that if we apply to polynomial 1, it is 1. If we apply to any square, it is non-negative. And if I apply to P multiplied by any polynomial, as long as the degree is not very large, then it is 0. And basically, okay, let me immediately say that expectation, true expectations over distributions over solutions are always pseudo expectations. But the converse is not true. So there are pseudo expectations. There are pseudo expectations of any degree. So whatever the degree I take, of course, all these properties will be satisfied by if I take a true expectation over the solutions. So
so if we have some distribution, we can just take an average according to the distribution. It's a kind of linear function on polynomials, a small degree or large degree, but it satisfies these properties. And then you want something else which satisfies these properties, but at least on small degrees of polynomials of small degree. Okay.
Yes. So now, what is good about pseudo distributions? I mean, there's the next thing will be even better. But this one is that if you have a sum of squares proof, and I already announced that our proof is actually a sum of squares proof, then pseudo distribution, pseudo expectations agree with that. So if I prove that f is greater than g, then pseudo expectation of f is greater than pseudo expectation of g.
Yeah.
So the degrees should be the same.
Yeah.
So yeah, I mean, and it is pretty clear if I just apply it, right? So I mean, I had sum of squares. I had either sum of squares or these guys, right? I apply it. I have something.
Yeah, you use linearity, which is given.
And then I mean, this is not nothing sophisticated here. I just
yeah.
Now, okay, now let me be informal, because formally that's a bit ugly, and no one actually does it for like. People usually when they apply sum of squares in papers, no one does anything except what I'm going to do today. So people usually refer in the very beginning that okay, there is an approximate solution, blah blah blah, and then people assume that there is an algorithm that outputs exactly this pseudo expectation. So that's why informal.
Okay, let's read this.
Yes. So first, we just again, this is a technical condition. We want the coefficients to be not very large. We want them to be polynomial.
Yeah.
And then another condition is kind of more important, is that there exists a solution, and then this solution is not very large. The norm of the solution, I mean, it can be very, very large, but not extremely large. It should be exponential due to the polynomial in this n plus k.
So the coefficients are somehow finite binary fractions, and the solution is exact solution still.
Yes.
When you say solution, it means that this is approximate solution, or it's just a
this is the exact solution to the system. And yes, of course, we assume that the system and our original system, it was designed from our input, right? So our original system has coefficients which are just some not very long.
But still, this solution is not finite by net fraction, but some abstract solution. Okay.
No, I mean, no. Again, the system is fixed, and the
Fixed,
capabilities
yeah.
of the system are, and that's why this exact solution is defined by the system with this whose coefficients are rational numbers with no.
Yeah. What I am saying that this V star is not a finite binary fraction. It has infinite precision.
No. Yeah, let it be, yes.
We just don't know it somehow explicitly.
Yeah. This
But we
is
just consider
some abstract solution. Yes, it can be.
Yeah.
Yes, we cannot hope for a rational solution for polynomial system, right?
Okay, then there exists an algorithm that outputs.
Yes, so that outputs something. Okay, a good approximation. Let me not explain what I mean here. Okay, let's assume informally that it outputs exactly the assumed expectation. That outputs something that is really close to it, but the measure of closeness is hard to explain.
No. Wait a bit. You say to which pseudo expectation? There are many pseudo expectations.
That satisfies the system. I said I think for P by this I mean that it satisfies this system. This is the only thing I need.
No, but there are many pseudo expectations.
It outputs some of them.
Just a good approximation to some.
To some, yes. So there will be some expectation such that my algorithm outputs something that is close to it, whatever it means.
Yeah. So, but of course the algorithms. So, what is the input of the algorithm?
The input is the system.
Just polynomials of degree at most L.
No, it is the system. It can be polynomials of like fixed degree, I don't know, and L can be large. In general, doesn't have to be. L is some parameter, so L is what we decide, and then we find the degree L pseudo expectation.
No, but this algorithm, what it means that this computes an approximation to a pseudo expectation. It means that first we get a polynomial, the system P.
And we get a system, and L.
And also we have some L and some polynomials of degree at most L.
What do you mean by some polynomials of degree?
But the pseudo expectation is a function, is a linear functional.
But it is going to be, yes, but it is a linear function. That's why it will have I don't know, m plus k. Like this would be you can vectorize it and write as a vector of this dimension.
Yeah. So what we really say that we can compute, I don't know, the coefficients of this linear functional, or if we are given
of this linear function in the standard basis, yes. In the monomial.
Or even if we're given an input of this functional, some polynomial, we can compute a value the same.
And, yes, if we have a polynomial again in a standard representation, we can just easily.
So there are two arguments somehow. There is an argument. No, it's given the system, we get a long vector, which is exponentially long, but we just compute the values.
It depends on L. In our case, L will be constant, so it will be polynomial long.
Yeah. So we have time to compute all the coefficients of this vector. Yeah, and we need them to be to one specific pseudo expectation for the system. So there's, for every system there is one pseudo expectation functional, and we compute an approximation to this.
I mean, in some sense, yes, already it is implied that there is some pseudo expectation, but it is easy, right? If I take a distribution that is just supported on this point, then of course the expectation would already be the pseudo expectation, and that's why the set of pseudo expectations is non-empty. This is already, but of course there are.
So, and we assume that P is consistent. There is a solution.
It is not only consistent, but the solution, yes, has to be also not very large. It's easy to define a system of quadratic equations where it will be double exponential. So this is what we want to avoid.
Or just doesn't have a solution at all. Yeah.
But even if it has, it can be very large.
Okay. So is it okay?
The third condition of pseudo expectation, I'm confused. So it says for all polynomials fi. So the polynomials there are m. So m is number of p polynomials of the
Yes,
of
number of constraints.
p1 in this curly p, and then you fix also m polynomials fi, or
No, for arbitrary polynomial, as long as the degree is not large, we require, we need this. We need that it is zero. Apply to
so
this.
you don't need index I.
Yeah, exactly. Yes, yes. This is
No,
Okay.
we need this index for the equation. So the system is defined by several equations. So we take some equation and multiply it by some polynomial, and still the resulting polynomial should have pseudo expectation 0.
No, but equation 3 should say for every I, for every f without subscript, pi times f has expectation
this is
0.
correct.
Yeah,
Yeah, okay, I get it. Yeah.
No, you can also say if you take a linear combination of all pi's with some coefficients fi's, which are small degrees, then the expectation of the sum will be 0. So whatever you do with
Okay,
this
sum.
polynomial
Okay,
is
yeah,
okay.
yeah.
Is okay to have it
Okay,
Yeah.
now maybe I should be a little bit faster, but okay, so this thing is quite easy. There is indeed a solution because we can take xi and all other corresponding variables for this system, and indeed they will not be very large, so they will have 2 to the polynomial of this 2 to the polynomial of d. So it's easy to verify that indeed the true solution to the system, like xi solution, the solution that is based on our original sample, is not crazy large. Basically, because we assumed at the beginning that the bit length is bit complexity of our input is polynomial ID.
Okay, let's believe in this.
Yes, then the algorithm finds like a constant degree. I don't know. Let's say, I mean, we will use degree 12, maybe, I don't know, something like that. Pseudo expectation in polynomial time. And this is just the announcement that our estimator will be just this guy. So we get this pseudo expectation from this algorithm, and we apply it to this variable that we introduced in our system. Basically, just the variable that actually should be the, like in the ideal solution, it is the average of z. So we apply pseudo expectation to it, and I claim that this will be an optimal estimator. And this
No,
is
but so the polynomials have real values. So the pseudo expectation is just one number.
no. So the expectation again is a vector that for each monomial it is a covector. Let's say, like if you represent polynomials of degree at most L as long vectors, then this is like a pseudo expectation. They live in a dual space, so they are also vectors of the same length.
So we take
So this
pseudo expectation of polynomials.
This is d numbers. So this is applied to each entry. Yeah, maybe I'm not. So there are like this is a d-dimensional vector. I just apply it to each of the. Yes, I see what you mean. So there are d polynomials, right? And I apply it to each of them entry-wise. Yes.
Yeah. No, this mu-z is what? Is just
is our variable, and in a true solution, if you look at the true solutions of the system, it corresponds to the average of our z, of our candidates, which were good candidates. And we know that this average is close to the original.
Yeah.
And now I apply to this, I apply this pseudo expectation to this variable, and I claim that it is actually also good and even as good as the solution to the system.
Oh.
I mean, this is not, you of course cannot see it right now from here.
Okay, yeah.
It's an announcement. Okay, now maybe let me not stop here. So this is about the Cauchy-Schwarz, that I can prove Cauchy-Schwarz for like in sum of squares. There is a sum of squares proof of Cauchy-Schwarz, which just says that there's a proof.
So you want to look that original proof is just the sum of square proof with some bounds on this degree, yeah?
Yes, yes.
Yeah.
So for that, if you remember, we used Cauchy-Schwarz.
Yeah, we use Cauchy-Schwarz, yeah.
Also, there is a Cauchy-Schwarz, and this is something new. This is what we are going to do. This is a Cauchy-Schwarz for pseudo expectations, and this is basically looks exactly the same as Cauchy-Schwarz for expectations. So this is. I'm also. I mean, we can like. You can see that the proofs are not very sophisticated. I mean, that technically you need to check something, but There's nothing, nothing other. It is also easy to prove by yourself. If you try, I just wrote it in a compact way.
Okay, okay.
So let me not stop here. So again, like we can use standard Cauchy-Schwarz for sums, or let's say for average, I can also put here 1 over n.
Yeah.
Can also 1 over n here. It also is still true. Then again, for pseudo expectations, the same Cauchy-Schwarz as for expectations. So again, this is the SOS proof that you have already seen. So
Yeah.
nothing really changed. I mean, I changed the first line, and I think this line also changed a little bit. I added this. Nothing else changed. I only added some numbers, and these numbers say what steps are actually not so trivial, where we need to verify something. And so basically, okay, let's start from the beginning. And now you already see that alpha is just a number. Alpha is a number, and W is a variable. That's why I had to write it in such a difficult way. So, and again, I need to write this fourth power because I want to use Cauchy-Schwarz for sum of squares, which I use here. And again, the non-trivial part here is not the Cauchy-Schwarz, but why we can ignore this. So before we just said, okay, it is 0. Right now, we cannot say it is exactly 0, but it is actually 0 in sum of squares. I will show on the next slide what does it mean. So then again, like this guy is now again, so we need to prove this polynomial inequality. Like we need to prove that this is actually not larger than this, because everything else is easy. This is sum of squares and this is sum of squares, so that's why I can multiply.
Yeah.
If I prove that this is smaller than this, I can multiply easily by this. So that's why that is completely fine if I just prove in sum of squares that this is smaller than this. Then the next one is just I need to prove that this guy is smaller than 2 epsilon. So basically, these are and the next step, what is non-trivial, everything else is I just add and subtract. This is there's nothing sum of squares here up to this point, and here I need to use this guy and this guy. That there is a sum of squares proof that they are not larger than this, but again, not very hard. We will see on the next slide. So
okay, so we can just believe that, but the last stage is you cancel, you use squares and say you divide by the square of norm, which is not.
So this step doesn't work anymore, but something similar. Yes.
Okay.
For the last step, we need to use pseudo expectations. Yes. And for the last step, so what I do, I prove, since I can prove this, I can also, I take my pseudo expectation, the output of the element, and I can apply it to both sides. And so I get that the expectation of this guy is smaller than epsilon by expectation of this guy. And then I just start writing down, like this is like quite easy. So this is non-negative, this is a square, so it's non-negative. Then I just open up this product, and it is just like for expectations. So I have like, this is the first term, then there will be a cross term, and the cross term is -2 this, and this term will be plus this, and -2 plus 1 is -1.
Okay, well, we cannot follow anyway, but what you say that this taking square root is not really, can be replaced by some reasoning with this square.
Yes, it can be replaced by this reasoning, yes. And I only use basically, so here I use Cauchy-Schwarz, and that's all. So I say, okay, this guy is equal to this guy, is equal to this guy, and this guy I already bounded. It is bounded from here. So basically that's all. Yeah. So some additional line of computation is needed. Cauchy-Schwarz for pseudo expectations is needed, but that's all.
So let me try to check whether I understand correctly. So we have some lemma, which says.
Wait a bit. Gleb, can you show the previous slide about your estimator SOS?
You mean with the this one, or?
Yeah. So by our lemma, we should give in advance some p, right? In this fact. And what is p?
No, that's what let me check how I understand properly. So let's go back. So we start with a system. We start with a sample. And we want to.
That is no p.
No p. We want to construct, we have in this y, we want to find this some z which are good.
Right.
these are good.
If you want to find some this, it is find 1 and 2, right?
Yeah, and if no, it would be nice to find some z that satisfies 1 and 2, and it
But that's
would be
impossible.
somehow impossible. But
That
it's
instead
nice to
we
find.
put some
Maybe
to the-
possible, but we don't know.
Yeah, it's impossible, but still, let's note that it's enough to have some solution for this thing, solution for the system PRME.
Okay, do we use the corollary or not?
No.
No, okay.
Somehow even we use something stronger than corollary, I guess. So what we
Okay.
do then, we use some fact, which the fact is not explained, that if we have a system, we can find not a solution to the system, but something kind of. So instead of finding one solution of a system, or even a distribution, some distributional solution of the system, we can find a family of functionals which simulates averaging over some distribution of the solution of the systems.
We don't find a fact, we find one
So
of
we
them.
use this system of polynomials
Yeah, we use
in our.
this system of polynomials,
Mhm.
and we cannot find any solution of this, but we can use this quadratic programming, semi-definite programming, to find something which is somehow behaves as a averaging, what is called pseudo-average, because it behaves like averaging over some distributions on the space of solution of the system. And then this pseudo averages are defined of polynomials of small degrees. So to know that we can apply the pseudo average instead of a real averages.
Sasha, but we have here more variables than we need. We need to take the average of the i's, right?
Yes. Yeah, I introduced this variable. It is not needed. In the end, we could also apply pseudo expectation to this, but just for kind of, I don't know.
But our pseudo averaging will output the average over
I
all
just applied to
solutions.
this variable. I just applied to this. This is a like, okay, these are actually different variables. So there are z1, zd. So these are just variables of our system. And then I apply, I consider these variables as monomials. And then I apply to these monomials this pseudo expectation. And then I have d different values, and this vector of these d values is the output.
So I think there are several steps. So if we have one solution of the system, it's okay. We can use it as solution. If we have not one solution, but some distribution on the solution of the system, it's also okay.
Yes.
We can take average according to this distribution, and this will still be okay, because for every point it's okay. Moreover, we cannot have such a thing, but we cannot find any solution, and we cannot find any way of averaging of those solutions by any distribution. But what we can do is to make pseudo averaging. And still, this will be okay, because this corollary is proven using only a sum of square proofs.
Not the corollary, but lemma itself.
Lemma is proven using sum of square proofs, and our pseudo averages are compatible with this type of proof. So whatever will be true for averages will be also true for pseudo averages. And so after we notice it, that this lemma is actually a sum of square proof, we can apply, we can safely use pseudo averages instead of averages.
And to the last slides, we have verified that, probably.
Yeah, so we have like
I see.
Probably it's too technical. Yes. So this is the proof that we have seen already. And I just say that, look, all the steps that we use are actually low degree sum of squares proofs.
And then so there is this kind of simple part, a relatively simple part, which is just checking these proofs and checking that they are proofs of small degree, sum of square proofs of small degree, and everything is okay. And there is another part which is probably much more difficult, as this what is called fact, why we can indeed find a pseudo average, because this is the algorithmic part, which is completely
super hard if you know ellipsoid method. If you if you are familiar with ellipsoid method, this is also not very hard, but it of course requires like 20-30 minutes of.
Okay, no, ellipsoid method is probably more than 20 minutes, but
if you know it, model ellipsoid method.
Okay, but there is also something which is called метод внутренней точки, internal point. It's it can be also used instead of ellipsoid and
can it be always used? I don't know. I mean, but maybe things are harder to prove, because with the ellipsoid method, at least you can see things if they are true or not, or what you can do.
yeah.
Because you need just larger ellipsoid, like you need some upper bound, some lower bound, and basically.
No, we don't insist you. No, just if you tell that you know this proof and can explain it, but it's much longer than any...
even to formally define what exactly is like, because we need to relax system a little bit.
Yeah. It's so you know all this, and it's not something transcendentally hard.
But what I have shown is exactly how it is done. So also people are not working with some more difficult objects. So this is exactly how the sum of squares proofs work. So people assume that, okay, there is an algorithm that outputs exactly this pseudo expectation and nothing else. So this is exactly what is always assumed in the paper.
And who invented all this?
Well, it's hard to say. I mean, there people refer to, there are references to different people. Like there is Dima Grigoriev. I don't know him in person, but people refer to him. But I mean, what he did in his papers is very, very far from this. I think this is just like people collectively, like, and then I think there was also Boaz Barak, and he contributed a lot to maybe like understanding.
So no, just historically. So Dima Grigoriev did this after ellipsoid method, or it proves something?
Yeah, of course, everything was after. Yes, it is 20, less than 25 years definitely. Definitely 20 years ago, it was maybe only like at a very early stage. Yeah.
So Dima Grigoriev worked already with this problem, not with some other thing which was occasionally used.
With sum of squares proofs. He worked with if you're talking about the robust mean estimation, then it is actually very, very recent. This is, I think, the first paper was 2016. I mean, the first paper with non-trivial results where the error does not depend on the dimension. But the first papers were surprisingly harder. Like the very first paper was already much harder than what I say. They tried to do something for Gaussian distribution. And for Gaussian distribution, the problem is actually like non-trivial in the sense that there is some difference of what we can compute in polynomial time, some small difference, and what we can do information theoretically for Gaussian.
And still for Gaussian distribution, we need to somehow use the fact that it's Gaussian. Here you use with something which is about for variance, and then it's clear that you can do something. But with Gaussian, just a bigger...
It's not only just something. You can, of course, use moments. This is one thing what you can do. Another thing is like there are other things, but the thing is that actually what happens right now, the most sophisticated thing there is that it is known, it is not very hard to show, that if the covariance is known, then you can basically assume that there is identity, of course. And then with identity covariance case is easy. So you really can do much more computationally there than in the general case. But for Gaussian distributions, and only for Gaussian distributions, or like they should really satisfy exactly the same relations on the fourth and the second moment. Only for Gaussian distributions, people can estimate first covariance robustly. First estimate covariance very accurately, and then use this factor estimate mean. And this is, of course, this is very tricky. And this requires very, very specific relations, very specific properties of the Gaussian distribution. So they don't work for sub-Gaussian distributions. They don't work for distribution over the unit sphere, even if they are nice enough.
Yeah. Okay. So maybe indeed the last thing which you can do is just give some reference where we can look for if If
Yes, so
it's-
there are two references, like the book on the robust mean estimation, and there is something about sum of squares, but not so much. So they focus on another approach of filtering.
Yeah.
They talk about sum of squares whenever you use moments and whenever you want to do it efficiently. You need sum of squares.
Ой, молодец.
Коля, выключи микрофон, а то не слышно. Я извиняюсь. Это самое. Yeah, so this is general things, and this is which year, more or less?
Yeah, so this is very recent. I think this is like 2023.
Yeah.
And this one, let me see, and this one is also not very, maybe 2020 or whatever, I don't know. Like, but definitely less than 10 years. Definitely less than 10 years. Yeah.
Oh, so there is some great big idea that if you have sum of square proofs, this means that you can apply
2019.
Semi-definite programming to something, to some problems when the required bound can be obtained with sum of square proofs.
Yes, exactly. So I mean, that was a little bit, yes, of course, there is another method. One doesn't have to prove this stuff with root epsilon. You don't need sum of squares. But anyway, anyway, you need this lemma. This lemma is needed. And then some other idea called filtering is possible to do. Okay, I cannot find it. Yes. So, but as I said, like for example, if you have a Lipschitz transformation of a Gaussian vector, you can do better. Let's say with quadratic number of samples, you can do epsilon to the 3/4. And the only proof I know requires sum of squares.
No, it's interesting that sum of squares is a kind of very mathematical things. We analyze some proof, and from this we conclude that there exists an efficient algorithm for doing something. It's very, very interesting. And how practical it is actually.
Sum of squares itself is not, I mean, it depends on, it is not, let me say like this. It is not, I mean, there were some attempts, and there are, for some specific problems, people were able to speed up it. But one thing is that usually if you have sum of squares proof, it also has additional properties, like it is super robust towards something else, like I don't know, you have some perturb entries or whatever. It has some other properties. Okay, so for robust mean estimation, I think kind of you cannot do something tricky, but sometimes for statistical problems where you don't need robustness, you can look at the sum of squares proof and do something better with some more sophisticated spectral algorithm, which is like
but still for your specific problem of finding the estimate.
Oh, then of course no. For this specific problem, filtering is much faster. You can do it. You can do it in near linear time, I think, actually. This problem.
Yeah, and so there is another, but so this algorithm is not really practical, at least not the best one.
Yeah, so there is a simple algorithm that is anyway faster than sum of squares, because sum of squares requires, I don't know, ellipsoid or something else. Maybe I don't know this inner point.
Yeah.
They are faster, but still, semi-definite programming is faster. And then there is a filtering which is not so, it is not super fast, but much faster. And then there are also ways how to speed up this filtering, but of course they're quite technical, so they make it.
And they were invented before the sum of squares approach, or after?
No, they were invented after, because sum of squares was mostly already studied. Okay, sum of squares in statistics was actually applied first time to this problem also. So to some formulation, some kind of this problem. It was like 2017, I think, where people decided to seriously apply sum of squares in statistics. And there were many problems.
And then other people invented some more practical algorithms.
No, it actually did not happen like this. I think
or
it
even
was
before
it was parallel. It was either 2016 or 2017 where the first algorithm for this exact formulation of the problem appeared, and it used filtering, and it was roughly the same time. But then it was clear that this proof is generalizable of sum of squares, for example, for higher moments. So if you can prove in sum of squares something about higher moments, which is non-trivial but sometimes possible on distributions, then you can do better than root epsilon. And it is not known how to do it without.
And also there are no practical algorithms coming of some.
I think no, I mean, but I don't think that people were really so interested in this. As I said, like there are some distributions for which it is known to be true that we can certify in sum of squares. For example, as I said, like for log concave distribution, for example, we can do it, and then we can get some a nicer balance. But again, yeah, it is mostly theoretical thing, and that's why I don't think that anyone was interested. I mean, many people were. I mean, first of all, people really try to understand what happens in the Gaussian case, and the Gaussian case is very well studied, and it's actually completely non-trivial. There are, as I said, information computation gaps and other non-trivial stuff, very different from this one. And yes, in the Gaussian case, of course, there exists a very like a very fast algorithms which are sophisticated and which have very good guarantees.
Okay, so we have some kind of glimpse of what other people so there in statistics is a big field, and it's always interesting what people are doing. So they are doing very non-trivial things, and this is as one can expect, and it's still one small hole through which we can look and admire what they are doing, even if we don't fully understand exactly what they are doing. Okay, so thank you very much. It's really very funny and interesting things, and how you can use this meta argument to prove to get an algorithm. It's very interesting. Okay, so thank you again. And do we have something for the next time? What are the plans? Kolya, if you say something, we don't hear you.
No, not the next time will be in 2 weeks. And,
okay, and we don't have specific plans yet.
we have. There will be a защита дипломных проектов.
Yeah. So there will be Kolya's students which will make a defense of their master thesis, and then you should send some announcement, maybe
Right.
even now, if you probably know already what they are doing.
Right,
So
right.
with some probability. So just send approximate.
In 2 weeks. In 2 weeks. And not all the next week, because it's again a holiday, like today.
Yeah. Even I think it's a holiday. Yeah. Even in France, there's for some reason they don't have this week. This is a holiday week. Yeah.
Okay.
Thank you very much, and see you in 2 weeks.
Yeah, nice talk.
Yeah,
Thank you,
спасибо.
Gleb.
Спасибо. Yeah. Ладно, пока.
Okay.